Hey there guys, we're going to start Unit 3 today, and this is Notes A. We're going to go over the different types of bonds, and then we're going to focus on ionic bonding for most of Notes A. Then we'll get into covalent bonding, which is a little bit more complicated. So an ionic bond is going to be made up of a metal and a nonmetal. So the first thing that you need to know is where do you find metals and where do you find nonmetals? How can you tell them apart? So it all has to do with the periodic table. The metals are going to be located on the left side of the periodic table and the nonmetals on the right side of the periodic table, separated by that stair-step line. So if you see one from each side, you know you have an ionic bond. An example would be sodium chloride or table salt. Sodium is in group 1, it's a metal, and chlorine is a nonmetal, one of our halogens. So if you put them together, you have an ionic bond, whenever you have a metal and a nonmetal. Let's go down to the covalent bonds. Covalent bonds are going to be made of all nonmetals. Could be 2, it could actually be more, could have 3 or 4 atoms involved. A good example would be nitrogen and oxygen, nitrogen dioxide, NO2. Both nitrogen and oxygen are nonmetals, and so when they bond, we call that a covalent bond. You could also have both types of bonds present in the same atom. So an example of that would be sodium hydroxide. This is why I stress knowing your things to know and love polyatomic ions. The first thing you have to figure out is where's the polyatomic ion? And you should recognize hydroxide as one of our polyatomics. So the bond between the oxygen and the hydrogen, that would be a covalent bond. But the bond holding the sodium to the hydroxide as a whole would be an ionic bond. So it actually has both types of bonds. So that would be an example of mixed or having both types of bonds. Ion to ion is an ionic bond, and then the nonmetals within the polyatomic covalent bond. So you need to be able to tell them apart. If you see a metal and a nonmetal, it's ionic. If you see a polyatomic ion involved at all, it probably has both. And then if it's all nonmetals, then we have our covalent bond. All right, moving on. We're going to focus just on the ionic bonds now. So ionic bonding is when we have a transfer of electrons. So one atom wants to lose an electron and another atom wants to gain it. Metal and nonmetals make good pairs this way. And so what happens then is you have one atom that's positive, or I should say one ion that's positive, and another ion that's negative, because one's gained and one's lost an electron. So what happens then when you have opposites? Well, as you may know, opposites attract. And so that attraction between the positives and negative is what's going to hold that ionic compound together. So let's talk about valence electrons. Where do you find the valence electrons? Those would be the outermost electrons, the ones that are furthest away from the nucleus. Those valence electrons will determine the chemical properties of an element. The chemical properties are all about the bonding, and the bonding is all about the valence electrons. So your valence electrons are going to determine how an atom acts because they're going to drive it to bond certain ways. So the valence electrons are in the highest occupied or the outermost shell of the electrons, and they're going to drive those chemical properties. All right. When you're looking at the periodic table, we've learned that certain families have a certain number of valence electrons. So for example, group 1 all has 1 valence electron, whereas group 2 would all have 2 valence electrons. And it goes all the way over to the noble gases having 8 valence electrons. So that means that if I have the same number of valence electrons, it would behave similarly in a chemical reaction. For example, having only 1 valence electron is ideal for bonding. It's going to be perfectly able to give up just 1 electron. That's not hard. So that means it's going to be very reactive. It's really eager to give up that 1 electrons. So your alkali metals in that first group are going to be really quick to react, and they're actually super explosive in water. Whereas if you put something that has 2 valence electrons in water, not as reactive. And that's because it's harder to get rid of 2 valence electrons than it is 1. So the idea here is that if you're in the same family, you would behave similarly, kind of like you would behave similarly to your real family. All right, let's look at the octet rule. So oct, as you might know, means 8. So 8 is the ideal number of valence electrons for an atom. So all atoms really want to be like the noble gases because they have the 8 valence electrons. They have a very stable electron configuration, whereas the other atoms having 1, 2, even 6 or 7, They may want to gain, they may want to lose. They want to find out how they can get to that perfect number of 8 valence electrons. So it's common misconception that the octet rule says that you need 8 valence electrons. Technically what it says is that you want the stable noble gas configuration, which just so happens to mean that you want 8 valence electrons. So you want to be careful. Technically, it says we want the stable electron structure of a noble gas, not just this magic number of 8. 8 didn't come from thin air. 8 came from having the s orbital full of 2 electrons and the p orbital full of 6 electrons for a total of 8 valence electrons. That's our goal. That's stability, and that's important for an atom. So they'll do whatever it takes, whether that means transferring in terms of gaining or losing. That may also mean bonding covalently, which we'll talk about in notes B. Whatever it takes, they're trying to undergo some kind of chemical reaction in order to get 8 valence electrons. So let's look at what that does to our sodium atom. So let's start with regular sodium. I want to write out the electron configuration for sodium so that we can see what happens when we gain or lose electrons. So we would start at the beginning, 1s2, 2s2, 2p6. That's going to get us all the way through neon. And then sodium has 11 electrons, right? So far we've got 2, 3, 4, 5, 6, 7, 8, 9, 10. We still need one more. So that's going to come from the 3s1 orbital. The number that has the orbital that has the highest principal quantum number, or that furthest out energy level. Remember, the principal quantum number means the furthest energy level. That's my valence shell. So sodium has 1 valence electron in the 3s orbital. What's going to be easier to achieve in octet? Losing that 1 electron or gaining 7 more electrons? What would be a lot easier just to ditch this one? So if we remove that orbital, now the highest energy level is the 2 for a total of 8 valence electrons. Whereas the regular sodium only had 1. So it may seem kind of weird that we're increasing the number of valence electrons. That's because we lost that entire third shell. Now let's look at a non-metal, or I'm sorry, a metal. No, this was the metal, sorry. Gotta get used to this projector. So this was our metal. We went from 1 to 8 valence electrons. Now let's look at our non-metal, like chlorine. So what would its valence electrons look like? So chlorine, if we start at the beginning, we've got 1s2, 2s2, 2p6. And then when you're on the third energy level, chlorine is all the way over in group 17, one of our halogens. So we'd go through 3s2 and then 3p5. It's not quite at the noble gases. Oops, not 2p, 3p5. All right, so let's identify our principal quantum number. That is the highest energy level. That would be the third energy level for a total of 7 valence electrons. All right. Now what's going to be easier for chlorine? If I'm at 7, gaining 1 more to have 8 valence electrons, or losing all 7 to get back down to the second energy level like sodium did. Well, it would be way easier just to gain 1. Instead of a 5 here, if we just gained 1, we'd have a 6, which is now a total of 8 valence electrons. So for the metal, it was easier to lose an electron to reveal, like peeling an onion, an inside layer that had a perfect octet. Whereas for the chlorine, the nonmetal, it's already very close to an octet. So it's going to go ahead and gain electrons in order to get up to the octet. So if one's gaining and one's losing, we'll have opposite charges, which kind of explains why they're very good together. All right. So we go from 7 to 8 valence electrons. All right, let's look at an example like silver. So silver is one of our transition metals, and the special thing about transition metals is their d orbitals are kind of the most important. So transition metals do a lot of really weird things. They're kind of almost always an exception. For example, when we learned the number of valence electrons, we skip the transition metals, and that's because they can have different numbers of valence electrons. So I want to use the electron configuration to kind of explain why their number of valence electrons can change and how that has to do with the d orbitals. So let's look at silver's electron configuration to start with. So the original electron configuration, if we went ahead, because it's pretty far down, let's go ahead and use the noble gas. The noble gas before silver would be your krypton, and then we would have 5s2, 4d9, following Aufbau's principle. So let me draw out just the orbitals for the 5s and the d. So 5s, we would have one block. And then how many boxes did d have? Like how many orbitals come with a d orbital? There would be 5. So let's go ahead and set up our 5 boxes. 1, 2, 3, 4, 5. For not the 5d, the 4d. All right, now let's place our arrows. So 2 arrows in 5s going opposite directions, and then 9 arrows in the d. So up, straight across, following Hund's rule, but then to pair the last 4, we'll go the opposite directions. And notice that I have one box that's not paired. Well, that's a really big problem for transition metals. They don't like that very much. So instead what they're going to do is steal one from the s, so I only have one electron in my 5 energy level. And that electron is going to go to complete the 4d orbital. This is better for the atom for 2 reasons. For one, it fits their need to fill up that d orbital. They really want their d orbitals to be stable, so that'll fix that problem. And then the other thing is the 5, being the highest principal quantum number, would mean that 5s is my valence shell. And so if 5s is my valence shell, that means I only have 1 valence electron instead of 2, which is going to make bonding much easier. So for an atom like silver, we're going to have some stealing going on here. Instead of S2, it'd be S1, and instead of D9, it would be D10. So this will happen for any transition metal that ends in the number 9. It will actually also happen if you have S2, D4, that will become S1, D5, because my 5 orbitals, being exactly half full, also has a certain stability to it. So there are actually 8 transition metals on the periodic table that end in either D4 or D9, which will experience this exception. All right. So we're going to lose that valence electron in the 5s. Okay, let's talk about ionic bonds themselves now. Now that we've kind of looked at how the electrons move around within individual atoms, let's start putting them together. So since we need opposite charges for an ionic bond, you're going to be dealing with anions, which if you remember have negative charges, and cations, which have positive charges. So they're going to attract each other since they're opposite charges. And you should actually know the term for that attraction. It does have a special name. It's a Coulombic attraction known as an electrostatic force. So they're not actually physically connected. They're just kind of magnetically attracted, for lack of a better term. The proper term would be electrostatic force, not a physical connection. So even though they're not physically connected, they are actually one of the strongest bonds. So we're going to talk a lot about bond strength in this unit. The main principle behind it is the greater the difference in charge, the stronger the bond. It all comes down to opposites attract, and the more opposite, the stronger the attraction. So ionic bonds are going to have the most opposite charges because they're transferring an entire electron as opposed to sharing, so they would be the strongest bond. All right, now when we join them, we want to make sure that we do that in a way that the positive and negative charges cancel out. So sodium with a +1 and chlorine with a -1 would be the perfect pair. But you can also bond things that don't have matching charges. It just won't be in a 1-to-1 ratio. The idea behind figuring out how many of each is always to make it neutral. So the positive charges of the cations have to cancel out with the negative charges of the anions. So we're going to kind of draw out what atoms are attracted to which other atoms and try to see what kind of bonding, basically what kind of coefficients, or not coefficients, subscripts we would have. So the idea behind this again, no net charge. We want the positives and negatives to cancel. All right, so let's try a few. So let's look at sodium and chlorine. Sodium was in the first group of the periodic table, so it had a +1 charge. So it's going to come as a set of 1 pluses. Chlorine in the halogens would have a -1 charge. So that means that we have 1 plus and 1 minus. That would pretty much cancel out 1 to 1. And so my formula would simply be sodium chloride, which bonds in a 1 to 1 ratio. Notice how this dot could just easily fit in and complete the electron configuration for chlorine. And then sodium would be revealing its second energy level. All right, if we look at the aluminum bromide, that's not as easy of a fix because you would still have a couple of electrons left over here. So you can tell we're going to need more of one than the other. This isn't an even canceling out. So the aluminum is in group 13, column 13 on the periodic table, which has a +3 charge. Then the bromine, being one of our halogens, has a -1 charge. Let's write this +3 actually as 3 separate plus signs. So now if we try to cancel those out, one of the plus signs would cancel with one of the minus signs, but that would still leave 2 plus signs, which is not okay. It has to cancel out 100%. So if I had 2 more negative signs, then it would cancel out. So what that tells me is I need one of this positive set, the aluminum coming as a set of +3. But then I need 3 of the -1s, the bromine coming as a set of -1. So the way you would write that is aluminum just once, but bromine 3 times. So the idea is to figure out how many of each atom you need based on the charges. Let's do one more this way. Potassium only has 1 electron, so it could fill in 1 part of the oxygen, but it wouldn't complete the octet. So how could we fix that? Sodium, being in the first group of the periodic table, would come as a single +1 charge, whereas the oxygen is actually in group 16. So that's going to have a -2 charge. That kind of looks like an equal sign. That's supposed to be 2 separate minus charges. So the positive can cancel with one of the negatives, but we would need another positive to cancel with the other negative. So we have the positive atom twice, K2, whereas we have the negative atom only once, K2O. All right. There is a less pictorial way to do this. You don't have to draw these pictures every time. There's a shortcut called the crisscross method. So I'm going to show you that with our next one. Let me just make a little room here. So now we're on this magnesium and the nitrate. You do still have to know what the charges are. So with magnesium, it's in the second group of the periodic table, so it will have a +2 charge. So I'm going to write Mg +2. Now nitrogen is in group 15, which will have a -3 charge. So I'm going to write N -3. Crisscross means exactly that. We're going to crisscross the atom. The number 2 becomes the subscript for nitrogen, and then the number 3 becomes the subscript for magnesium. So I'm going to write Mg3 and then N2. So that means that I would have 3 magnesiums and 2 nitrogens. Notice that I didn't bring the negative or positive signs down. I'm just bringing the numbers across in the crisscross. Let's draw this out so you can see it's the same. Magnesium comes as a set of +2s, right? So if I had, by the crisscross method, it tells me I need 3. That gives me a total of 6 positive charges. But then with the nitrogen, it came as a set of -3s. 3 negatives. So I would need 2 sets of those, according to the crisscross method. So if I have 6 positives and 6 negatives, then they would all cancel out. The crisscross method tells you exactly how many you would need in order to do that. So we'd have Mg3N2, and it does fix my cancellation problem. So let's try the last one doing that way. We've got our potassium, which would have a +1 charge. And then we have our phosphorus, being in group 15, would have a -3 charge. So using the crisscross method, how many potassiums and how many phosphorus? So the plus is understood to be a 1, which would be my subscript for P. By the way, a subscript of 1 is also understood. So P with an understood 1. Whereas my 3 would then be the subscript for the K, so I would write K3. K coming as a set of 1 would have 3 separate positive charges, which would cancel out with the -3, or a set of 3 negative charges for the phosphorus. So the answer for the potassium and phosphorus mixture is K3P. Final answer. All right. So we have NaCl, AlBr3, K2O, Mg3N2, and K3P. Final answers. All right, so with the crisscross method, the idea is you're bringing the charges down as subscripts, but don't actually bring the positive or negative. You've never seen a plus or a minus on the bottom, the subscript area of an atom. It doesn't belong there. It's just giving you kind of a shortcut for the ratio. The other thing that you have to be careful of is with your polyatomic ions, you want to keep them isolated. So I would recommend putting parentheses around your polyatomic ions. So let's try one of each. So calcium chloride is very similar to the last two that we did. The calcium, being in the second group on the periodic table, would be Ca+2, and the chlorine, being a halogen, would be Cl-. So when I crisscross, the 2 becomes the subscript for the chlorine, Cl2, and the minus, or -1, becomes the subscript for the calcium. So it ends up as CaCl2. And that would cancel the 2 positive charges with now 2 of the negative charges because of the chlorine, or because of the subscript on the chlorine. Let's also try one with a polyatomic ion, magnesium phosphate. So magnesium is in the second group of the periodic table, so it's Mg+2. But then phosphate is one of your things to know and love. So you're supposed to be able to know what phosphate is off the top of your head. So phosphate is PO4 -3. The charge was part of what we memorized. So now when we crisscross this, you're going to take your -3, or the 3, to be your subscript for your magnesium, Mg3. The tricky part is with the phosphate. The 2 is the subscript for this entire phosphate. So you're going to write your PO4, and the 4 is part of the phosphate. I'm going to put that whole thing in parentheses, and then put the 2 on the outside there. Mg3PO4-2, where that entire phosphate ion is in parentheses. This is super important with polyatomic ions that don't have subscripts. So let me give you just one more example. I know this isn't in the note takers, but let's do magnesium, which is +2, and hydroxide, which is -1. This 2 would go on the outside of the hydroxide. -1, my magnesium would just have a -1 subscript, and then with the hydroxide, I need this 2 subscript. If you forget your parentheses, that means that there's only 1 oxygen and 2 hydrogens. That was not our intention. The intention was for there to be 2 hydroxides, which should also include 2 oxygens. So you absolutely have to have your parentheses around it in a situation like that. This would actually be counted wrong if you forgot your parentheses. In an example like sodium hydroxide, where it's +1, -1, and I don't need subscripts on the outside, it's okay to leave off the parentheses, but I wouldn't count it wrong if you'd include them. I'd rather you have them than not have them. They have to be here in some situations, so I think that's more important. So basically the bottom line is put your polyatomic ions in parentheses. All right. So there was our magnesium phosphate. So now I want to kind of apply this idea to figure out charges for transition metals where it could be different. So I've got these three compounds. I have iron attached to oxygen, but in lots of different ratios. Quick side note, this wouldn't happen to metals in like group 1, 2, or 13 because they have set charges. But with the transition metals, they can have different charges, or to be more technical, can have different oxidation numbers. All right, so let me pick a different color. Let's go with my iron oxide first. Now I don't know the charge of the iron. That's the whole point of this, right? But I do know the charge of the oxygen is -2. The other thing I know is that the overall charge should be neutral. I should have no charge left over once the molecule is formed. So the question is, what is it that iron would need to have in order to cancel out a -2 charge? And so that would be a +2 charge. Iron in this compound would have a +2 charge. All right, let's try the next one. Again, we know oxygen has a -2 charge, but there's a catch. This time I have 2 oxygens, so that's going to have a total of -4. So then what would iron have to cancel out this -4 charge, or the total negative charges? It would need a +4 charge. That number actually gets incorporated into the name. This would be iron 2 oxide. This would be iron 4 oxide. So we want to be able to tell them apart. All right, last one's a little bit tricky. Let's go here. All right, so we know the -2, no, that's not a good color. Just trying to do different colors. We'll just go back to purple. All right, oxygen's -2, and I know the entire compound needs to be neutral. So then what is it that I would need to have in my iron area in order to cancel out the -2? This entire thing would need to be +2. But there's a catch. In this last compound, we have 2 iron atoms. So if I need a total of +2, what would each iron atom have since there's 2 of them? In this case, a +1. If each iron atom had +1, 2 of them would have +2, and that would cancel out with the -2. So this would be iron 1 oxide. So the only way to tell what type of iron you have is to look at the anion and work backwards. Start with what you know, and then use that it's supposed to be neutral in order to determine the charge of the iron. So +2, +4, and +1 in this case. All right, guys, that's the end of Notes A for Unit 3. Our next notes, Notes B, will be all about covalent bonding, the other type of bond where we're actually sharing instead.